Alright, welcome to my newest LeetCode video where I go through and choose a random LeetCode for the very first time and just go through my process for solving it as I would in a real technical interview. Today we're going to do a random medium, and you know what? Let's do the daily maybe. Just see what that one is. I don't normally do the daily ones, but let's just try. So let's get the timer ready. Let's begin and start reading. So we're given an integer n and we want to return the least number of perfect square numbers that sum to n. A perfect square is an integer that is the square of an integer. In other words, it is the product of some integer with itself. For example, 1, 4, 9, and 16 are perfect squares, while 3 and 11 are not. Alright, let's just write that down. So, given int n, return the least number of perfect square numbers that sum to n. Instantly, this sounds like, is it the knapsack problem? Or one of those coinage problems? I don't know which one it's called. But dynamic. How do you spell dynamic? Dynamic programming definitely seems appropriate here, but let's just go through the examples. So if we go n says 12, our output is 3, as we can get to 12 by summing 4, 4, and 4. 13, we can get there in 2 by summing 4 and 9. So dynamic programming, no, that's actually the wrong word. I'm thinking of greedy heuristic. Instantly I'm thinking, or is it a bit of both maybe? Would it be both or just sort of greedy recursive? Either way, I'm just gonna write my thoughts out. So start with the largest number, largest perfect square below or equal to n, and then see if we can get the new number with squares. So if we go for our n equals 12 example, we would first try 9 plus something, which would have to be 3, and now we can't get to 3 unless we did 9 plus 1 plus 1 plus 1, which would give us 4. Otherwise, we would then try the next lowest one, which would be 4, and then we would try 4 plus 9, which doesn't work. That goes too high, so we would do 4 plus 4, and then plus 4 again, which would give us our answer. Otherwise, we might try something like this along the way or afterwards. Or no, we would never go below it again because that would mess us up. That makes sense. I have not explained that very well. So what I mean is we start with 9 in this case, and then we would check if we can add 4. We can't, and then we would check if we can add 1 and 1 and 1, and then we do it. And then we go to the next. Do we go to the next lowest 4? I mean, we do, but how do we know that? Oh, it's a bit tricky in my head. It's a very simple problem that I can tell, but just how to do it. Well, I'm gonna write out our perfect squares. We probably can just calculate them after. Yeah, just so I can visualize it, and then we can change it after. So it'd be 1, 4, 9, 16, 60. No, not 64 is the next one. 25, 36. Okay, this will take too long to do, I think. But we'll just keep going. As it has to go up to 10,000? 100,000. So that's too much. But we'll just do a few just so we can see. So 49, 8 times 8, 64. 5 times 1, 100. We'll just do the first 12. And then maybe there's dynamic programming to keep track. Ooh. If it's anything, it'd be one-dimensional dynamic programming, which is the quickest way we can get to another number. Okay, my brain's a bit fried, but with dp, it would be 1d dp. dpi stores the least number of perfect squares starting to get, and then at the end we return dpn. So just filling up dp there is our big issue, but we could do a recursive stretch where we just update n, I think. As my brain's a bit fried, in a real interview you don't really want to start coding before you've got the actual algorithm sorted out in sort of pseudocode and explained first. You'd always want to get that sort of before you even start coding, but as my brain's a bit fried, I think I might just start coding. It's just LeetCode practice, so I don't think it's the end of the world. It's more important. I don't know if it's more important to get the actual solution or do all the right things. Because in an interview, if you get the right solution but you do everything wrong and the interviewer can't follow you and all that stuff, that's pretty useless. But if you do all the right stuff and you just can't manage to get the correct answer, I think that's totally alright. But it's just LeetCode practice, it's not the end of the world. So let me just try and start coding to see if it helps me at all. So we need a recursive thingy, returns nothing. Just call it recursive for now because that's what matters. We've got our new n, or we should call it I maybe, so it matches up with sort of that step. So oh no, it also needs to take in our dynamic programming vector, I think, otherwise we could have it out of any of the functions, but I'm not sure. Anyway, do we need to initialize it or not? I don't know. So have to call recursive from there and then just return dpn. So now we just have to worry about our recursive function. So what's our base case? When what? Okay, I'm a bit stuck. I'm not sure what we could do. Oh, it's annoying. My brain is completely fried, but I want to get this done. This is really not good. It's 10:40. My brain is turned off, so I'm not sure how to do this. Trying to think. I don't want to use a hint, but I might need to get a hint. So we start with the. I'm just trying to figure out how to get my approach into actual code. I don't know if it's the best case we need to worry about, but if DPI exists, I guess maybe we should initialize it. I can't remember which order the parameters go in. I think the number of elements first. 0, we said 0. Do that. So if DPI is not 0, you want to return something, then don't we? So maybe this actually needs to return the integer. I don't know. And if we start steps at 0, and now our main thingy here is, do we need to keep track of the steps maybe so far? I don't know. Okay, what's another base case? Because we definitely need another. Pretty much if they're equal to a perfect square, I guess. But there's that. Guess if I equals square, return 1, yeah. 2, 4. So if I is a perfect square, how do we know that? I mean, maybe, if the square root's an integer, would that work? Or divided by itself? Is it? Hold on there. If 16 divided by itself doesn't do anything. If 16 divided by square root, is it square root? No, because that's just a square. What am I talking about? I guess, yeah, if it's square root is an integer, but how do we know that without it converting to an integer itself? No, we can just have it for now. I don't know. Is an integer? I don't know how to know if it's an integer. Well, we'll do this for now. We can always come back and change it. We would set. So actually, check this one first. We'll just do that. Steps +1 return. Steps +1 maybe? Or do we do that? Hold on. Oh, now I don't know. I don't know. Oh dear. Ooh, not good, not good. I don't know if this needs to be here or somewhere else, but I don't know. Oh dear. So we want to start with a square root less than square root of, I don't know. I'll just write any thoughts I can and then I might have to look for a hint. Start with the I'm not sure. I have to look at a hint. Well, let's double check I'm on the right topic. We're greedy and dynamic programming. Breadth first search, what the heck? Oh, not good then. Breadth first search terrifies me. Why would we need to do that? I don't think there's much hope for me. Let's look at the discussion though. I thought of that. This looks like a pretty tricky math question, actually. Is there an editorial? No. Okay, there's 4 different solutions in C++, which is good. Let's just go through these and try to understand them. So the first one's dynamic programming, the second one is static dynamic, the third one's full maths, which is annoying, and the fourth is BFS, which looks crazy to be able to work that one out. Let's just go through one by one and see if we can sort of understand them. So, okay, I'm just reading that. Let's think about the dynamic programming one, which I guess is probably the approach I was going for. So, num squares n. Straight away, if n is less than or equal to 0, we want to return 0. Okay, that. We want our DP table. Just got DP, I guess. N plus 1. Not sure why the plus 1's needed. Let me make it massive for some reason. And we set the last one, or the first one to 0. We need 0 steps to get to 0. Fair enough. And we go through each number up to n. So I guess this is a really long way of doing it. Okay. And then we go through each number. Oh dear, this is weird. J starts at 1, while j squared is less than I. Keep increasing it. And then I equals the minimum. Oh yeah, that's what I forgot as well. When you update it, you just need the minimum. Yes, update in the DP table with the minimum of what was already in there and what you just found. So I DP I take j squared plus 1 for whatever reason. Let's make sure this works first. Surely this is dpn, doesn't have to be the back, does it? Maybe it's n plus 1 or something there. Okay, I don't really understand this one. Not great. So it works. My first ever daily I've done. And it works fairly quick as well, which is actually surprising. So just to understand it, I'm going to ask ChatGPT to add some better comments than that. So let's see. I have a solution to LeetCode 279 perfect squares and lots of. Hopefully this helps. Looks pretty good, pretty good. We don't need that because the constraints is ends always at least one. Yeah, let's just put that there. Now we want to initialize our DP table. With size n+1, where each element will store the minimum number of perfect squares, which I have sum of I. That's pretty self-explanatory. The base case makes sense. Don't really need to explain that one. Loop through all numbers 1 to n. Each number I loop. Loop through all perfect squares less than or equal to I, excuse me. And then date dpi with the min of its current value and okay, so dp I take the perfect square plus 1. That doesn't really explain my head. So let's copy this and then read it out. So dpi take j squared is the minimum number of perfect squares needed to form the remaining number. I take j squared. And then we add one to account for the sum. That makes sense. I'll try to explain that better. Oops. So for each number 1 to n, we loop through the perfect squares below the current number I. And then so we minus that perfect square from I, and then if it takes less steps to get to that remainder plus 1, we update dpi. Alright, so I kind of get it. I think that's just more practice needed for me. And then that result is self-explanatory. For me to understand that is just more practice, I reckon. It's annoying though. That's a nice, simple solution. I'll submit that just so we've got it saved. And it seems quick enough already, but let's see what the rest of them say. So static dynamic programming is much faster apparently. I'm not sure why that was 440. And when mine's so short, but oh well. Let's see what this static one is. So you don't need this part. That part looks pretty much the same. And I'll write it out just so we can see. So the dynamic table is actually static for some reason. I'm not very used to that. Starts at just a 0 apparently, and we just do while size is less than equal to n, keep adding stuff to it, I guess. So side, right, squares, max. Ooh, this is confusing. And we go through each perfect square. Update count squares. And then, okay, I'm just typing it out and then I will really try to understand it in a second. Oops. Push back. Squares. Alright, let's run that, see if it works first and foremost. No, because we've got too many curly brackets. Alright, so that works. So we initialize our dynamic programming table, and then while the table isn't full, we set m to be the size of it. So m is our target number, I'm guessing. Our target number. Knit the number of squares to n as pretty much infinity, and then we want to loop through all squares up to m, and then we set squares to the min of itself and the number of steps to get to m minus the current square plus 1. Okay, I think I get that. And then add let's submit that, see how speedy it is, how fast it is. Much faster, very nice to see. I understand that fairly well. It's that looping that I missed, that I couldn't quite think of how to go through each perfect square. That's why I sort of thought about putting them in an outside vector. The mathematical solution, I'm not going to really go through these, I'm just going to read them, because I think in a real interview, getting a mathematical solution normally either means you're really good at maths or you've sort of seen the problem before. I don't think it really shows your problem solving skills. I mean, it can, but I think you'd have to be quite a whiz at maths. So it's based on the whole, on that theorem that it's either 1, 2, 3, or 4. Okay. So if it already is a perfect square, return a 1, which is sort of what I was thinking about earlier. It's just that one tiny little check. And to do that, you would do the square root of n. Okay, so I sort of thought about that. So you get the square root of n, and then if you times itself and it equals n, then it's an integer. That sort of avoids the, I guess it would avoid the integer rounding thing with these types. So the result is 4 only if n can be written. Okay, yeah, so this is just crazy. You need to know the theorem. You're not really going to get this otherwise. Unless you're a legend of math. And then that's also using bitwise operations, which I'm very bad at. Anyway, the BFS solution is crazy to me. How could you even know you could do that? So you've got your perfect squares. Let's just have your numbers. You've got your DP table, I'm guessing. Yeah, well, pretty much. And then, okay, you fill up the perfect squares by just going through that. Alright, I didn't even think of that. I should have thought of that. Alright. And you also do that. Which is interesting, but then that makes sense. Consider a graph that consists of numbers 0 to n as its nodes, j's, goes to I if j was I plus a perfect square, or the other way around, so node 0 to BFS. If we reach node n, let's take n, we need least number of perfect square numbers, which sum to n is m. Here, since we've already obtained the perfect square numbers, we've actually finished the search at step 1. What the heck? So we've got our Q for BFS, we put in the H perfect square. What the heck? I'm not sure if I can even understand this. So I go through each level. Temp is the front of the Q. Then you go through each perfect square again. And if our temp plus j's a node, then we can get there in one step. Alright, I sort of get that part. This else if looks scary. If temp plus j is less than n, and temp plus j equals 0. What does that mean if it equals 0? That means we haven't seen it? Or what? Guess maybe it means we haven't seen it yet. I'm not sure about that part, that equals 0. But I know that means it's not the first time we've seen it. I don't get it. Oh, I'm not sure if that's super easy to understand. But I like the static. The dynamic programming was what's the word? Approaches there. Alright. I guess that's another weak point for me that I need to go out and practice. Hopefully that wasn't too painful to watch. Because I didn't do very well at all. But hopefully you learnt a bit. I definitely learnt a bit. I've learnt that dynamic programming, I was right there. I only got stuck on going through the options of perfect squares, which I mean makes perfect sense there, to be honest. Yeah, it does. And I'll let that. Maths solution is crazy to get if you get it. And there's also a BFS solution, which is apparently slower than this one. But I hope you enjoyed watching this video. If you did, be sure to leave a like and subscribe with the good stuff. Comment any feedback you have, anything like that. And yeah, I'll catch you in the next video. Alright, thanks.